So this is a preliminary video where I want to discuss the Ceph architecture. And if you can't quite follow along, don't worry about that. But I wanted to put this out there first because I reference this a lot, even in the early material, and it won't really probably make full sense until we get into the later material, unless you already have some exposure to Ceph and storage that's distributed with objects, not in the sense of object storage like Amazon or Swift or one of those technologies, but in objects on disk that get distributed across multiple disks. So let's talk about this core architecture. And this diagram, it's a really good diagram, but I'm actually going to start at the bottom. And I think that's going to make more sense as we work our way up the stack. So at the bottom, we have RADOS. And RADOS means Reliable Autonomic Distributed Object Store. And that's a fancy name for a Ceph cluster. So you can see at the bottom of that box, it actually has the description, self-healing, self-managing, intelligent storage nodes. The layer on top of that is LibRados. And what this is the programming interface to the Ceph cluster. So everything that talks to the Ceph cluster has to go through a library. This library then makes calls directly into the Ceph cluster and allows you to write data to it, etc. There's a lot of libraries available. You can see on the chart here, there's libraries in C, C++, Java, Python, Ruby, and even PHP. So there's a lot of different ways that we can read and write data to our Ceph cluster, which is good because there's a lot of different applications out there that we might, written in different languages that we might want to utilize Ceph for storage in. So the layer above that, RADOS Gateway, RBD, and CephFS, these are three technologies that use LibRados that come with the Ceph cluster. The Ceph backend down here, this guy, stores data the same no matter which client you use, whether you're using CephFS or RBD or any of these good ones. And I don't make the best arrows with my mouse, so hopefully they make sense. So let me walk through these three, and then there's other ones out there. People have written their own in Python and C, and there's a PHP, obviously. So all these technologies exist, but the three that come with it are the most important to touch on for our purposes. So RADOS Gateway, we can see in the description, it's a bucket-based REST gateway compatible with S3 and Swift. What this basically means is it allows us to use the Ceph cluster for object storage. A RADOS gateway is, you can think of it as a web application that a client can then talk to send and retrieve data from in the same format as Amazon S3 or Swift object storage. And the way that that works is the client either sends or requests a file, and the file has a full HTTP address that it can be referenced by. RBD, RADOS Block Device, is a block device in the traditional sense that can be attached to a virtual machine, and to the virtual machine it appears as a hard disk. So you can see here in the description, a reliable and fully distributed block device with a Linux kernel client and a QEMU KVM driver. So what this means, on a Linux bare metal machine, a machine that's not virtualized, you can attach RBD devices. I shouldn't actually use the word attach because that's a virtual machine technology description of how we attach storage. You would basically mount RBD as a disk device, format it, etc. Then you can read and write data to it on a bare metal system. And we're actually going to do this in our lab. Now, for the QEMU KVM driver, this is really important because a lot of you are probably looking at Ceph for block storage for, say, OpenStack or CloudStack or one of these other virtualization technologies that's emerging right now. So it's important we have this QEMU KVM driver because that's the default virtualization technology for something like OpenStack, and it's built into Linux and hooks directly to the Linux kernel. And QEMU allows us to attach one of these RBD devices, or a couple of these RBD devices, however many we need, to a virtual machine. Once it's attached to the virtual machine by QEMU, we don't mount this the same way that we do on the bare metal. Once we attach via QEMU, then we go into the virtual machine, and here, because it has the appearance of bare metal, because it's a virtualized operating system, then from there, we can mount the device as, say, dev SDB, dev SDC, etc., format it just like a regular hard disk, mount it to whatever location we need, and then we can read and write data to it. The third one, Ceph FS, is Ceph File System. It's a POSIX-compliant distributed file system with a Linux kernel client and support for Fuse. What this basically means is this is a shared file system that any client who has the proper privileges can mount. And typically you would mount this via NFS. There's actually a Ceph FS driver that's similar to NFS that you mount this file system. And then you have directories. So you mount it to a particular mount location, then you have your directories. And anybody can mount that particular file system point and see the same directories as you, and you can read and write files and share files. So it's really just a file sharing subsystem, basically. What the two different ways you can mount this file system is either with the Linux kernel client, which is what I originally referenced, CephFS client, or Fuse. Fuse is a generic Linux file system and user space application that you can mount a lot of different types of file systems with the Fuse client, but it adds another layer on top of the application stack, if you will. So the performance isn't as good if you use the native kernel client. So we really want to, if we can, avoid Fuse. So moving on, covered this. We covered those technologies. We covered LibRados. So now let's look at how this actually works. So no matter what client library or method you use to read or write data to Ceph, Ceph doesn't care because that's an abstraction. On the back end, in the actual RADOS cluster, Ceph stores the data the same, no matter what format it comes in via object storage or block storage or Ceph file system storage. So the way that the cluster works, we've got our little smiley face guy up here. He's our client. And then we have our mons over here. These are our monitor servers. There are three different components to a Ceph storage cluster. There are the monitor servers, which keep track of the cluster state. There are the storage servers, which are also known as OSDs, object storage daemons, and they attach to the actual hard drive, and they're the ones doing the reads and the writes to the hard drive. And then there's the metadata servers, which you need if you're using Ceph file system. Now, the metadata servers are not a required component, whereas the monitor servers and the object storage servers are. So really, you only need two out of those three technologies to get a Ceph cluster up and running if you don't want to use the file system capabilities. So, okay, over here, just talked about that. So mons store cluster configuration maps. So the client talks to the mon and says, hey, you know what? I need a copy of the latest status of the cluster. The mon keeps track of this. So if a disk failed, the mon effectively removes it from the configuration because we don't want to write data to it. And this becomes important because it's actually the client, this guy, smiley face guy, that determines where the file is going to get written. So the client doesn't talk to the server and say, hey, where should I write this? The client actually has an algorithm that once it has the configuration from the mon server over here, it can determine and calculate where it should store data. It's pretty intelligent, and this brings the mon out of the data path, so there's no bottlenecks on storage speed. Okay, so moving on. I think I got ahead of myself here. So here are our clients that we talked about on the first screen. We got block storage, file system, and RADOS gateway. And those all sit on top of LibRados. LibRados, again, is that programming layer that sits in front of the cluster itself. So these objects here are the data that we're receiving from these clients up here, these guys. Try to do a little underline there. So this gets abstracted by LibRados and then gets written as these objects to the storage cluster. So you can think of an object almost as a particular file. And this particular file gets replicated across a bunch of different storage devices, and we're going to get into how this works. So when you create a storage pool, and the storage pool is basically a particular amount of storage, not in size, but although you can limit size, it's a particular chunk of storage that you're kind of grouping together and then presenting to the client. And you can have as many pools as you want. So say you want to have a pool just for your virtual machines for your accounting department. So you would create a pool and you would say virtual machine accounting department for the name, and then allocate that pool just for their usage. Now, pools are comprised of placement groups. And the number of placement groups you use multiple placement groups per pool, really is determined by how many storage devices you have and monitors and all this other good stuff. And there's an algorithm surrounding this that we'll look at later. And what placements groups do is allow you to replicate data across all these storage devices. And the reason for that, if we were to replicate individual files, these little objects, there would be a lot of churn every time one of these gets updated. So the way that Ceph works is the data is actually encapsulated in a placement group. And it's the placement group that gets replicated. So say each of these three files happen to get updated, well, it's going to replicate this whole placement group. So whatever objects within this placement group got changed, it's going to copy over. Now, this is a really fast process, so you can actually argue about the objects, but the placement groups allow for a faster lookup to find the object. Because we know, hey, there's a pool. This pool is comprised of placement groups, and there's actually mappings of the placement groups, and we know which objects reside within those placement groups. So this allows for quicker lookups rather than just having, say, one big directory with all the files in it that we need to iterate to find our file or our object. So the OSDs at the bottom, these are the storage devices. And I picked a couple random numbers because in our storage cluster, we're going to have a lot of disks, hopefully. If you're doing a test cluster, maybe you have 3, 6, 9, 10, 12, whatever. So down here, we'll pretend we have at least 49 disks in our cluster. So OSD is a software daemon that runs on Linux. And there's one OSD that runs per each disk that you use for storage. And the OSD, that particular OSD daemon, is attached to that specific drive and manages that drive. It also talks to the other OSD daemons when it needs to do replication. So placement groups get written to OSDs. Now, you're not going to have one placement group sharded across different OSDs. You're going to have one whole copy sitting on OSD 12 and another whole copy sitting on OSD 49. And you can see our little funky lines in there. That basically is saying that data is replicating this placement group, or I'm sorry, the OSDs are replicating this placement group between these two actual drives. Now, with placement groups on the disk, there is one placement group that's considered the primary, the authoritative placement group, and then that gets replicated out to slaves or secondaries, however you want to refer to those. In the case of placement group 2, the same thing occurs. We've got one copy, and we'll call OSD 1 primary and then one secondary on OSD 27. Now, this can get interesting because as we add OSDs and OSDs are less utilized, then data actually can shift over to these new OSDs. So if we're on an OSD that's really crowded, let's say our whole cluster is really crowded and full, and say we had a dozen disks. Well, Ceph is going to be like, hey, I've got these new disks that nobody's touching yet. So rather than having this storage that's locked to a specific disk, Ceph's going to do some operations in the background to replicate this data over to another disk and make that, say, a primary. So let's say OSD 12 is full. We add OSD 1, let's pretend that's a new drive that we add, which the numbers totally don't make sense for this, but for the sake of our little demonstration, let's ignore that. So OSD 12 is full, OSD 1 is not. So this Ceph is going to see that the performance of this is starting to lag and that it's really full, but this is available. So Ceph's going to do what's called peering and start copying that data over to that other OSD. So at that point, then we're going to mark this as gone effectively, And this could be a primary copy, and then say we could even replicate that over to 27 as our backup copy. So that's basically the gist of how a Ceph cluster works. Again, if you don't fully understand it, don't worry about that yet. We're going to cover this in really heavy detail as we progress in the course. I just wanted to at least throw this out there just so you can kind of see how the data flows from the client through one of these technologies to write then to LibRADOS, which then LibRADOS does not care about how the data was sent to it. LibRADOS then says, hey, I have these objects. Objects are encapsulated within placement groups. Placement groups are encapsulated in a pool, which I don't have on the diagram. And placement groups are writing to OSDs, which then replicate. So that's the quasi-quick overview of how a Ceph cluster works. And let's go ahead and jump into the material, and hopefully this will clarify itself as we move along.